Student friends, now we are going to discuss one of the important formula in the theory of the radiation, and that formula is Planck's radiation law. We have discussed the black body radiation spectrum, and we know that the nature or behavior of the black body radiation spectrum and the behavior of the black body radiation spectrum cannot be completely explained either by Wien's distribution law or Rayleigh-Jean's law. Rayleigh-Jean's law shows the agreement of the black body radiation spectrum in higher wavelength region. In low wavelength region, it deviates the behavior of the black body radiation spectrum, and Wien's distribution law is in agreement with the black body radiation spectrum at low wavelength region, but it deviates in high wavelength region. So these two laws or these two theories could not explain complete behavior of the black body radiation spectrum, and hence the Planck, by introducing a new concept, a new idea, he obtained a formula which is called as the Planck's formula, and that Planck's formula completely explains the behavior of the black body radiation or that black body radiation curve. That formula or that theory now we are going to discuss. Now Planck's radiation formula for the black body radiation spectrum, it is based on certain hypotheses. So the first hypothesis made by Planck's is that so the black body radiation chamber is not only filled with radiation but also with simple harmonic oscillators. They are called as Planck's oscillators, and these oscillators oscillates with all possible frequencies. Means if you consider a black body radiation chamber, then the radiations are there, but the radiations they are assumed to be nothing but due to the simple harmonic oscillators, and these are called as Planck's oscillators. Another hypothesis on which this radiation law is based is the oscillator of frequency nu. Any oscillator, it is a simple harmonic oscillator, and it has suppose frequency nu, then it will either absorb or emit the energy in the units of quanta of magnitude h nu. Means the energy will be absorbed or emitted in the form of quantum of energy, and that unit is h nu, where h is Planck's constant. That means the energy is neither absorbed or nor emitted continuously, as we discussed in classical theory, but it is absorbed or emitted in the sets of certain values, and those values are nothing but multiple of h nu's, including 0, means either 0, h nu, 2h nu, 3h nu, and so on. So that means these energy is absorbed or emitted in the multiples of small unit, and that unit is called as the quantum, and that quantum of energy is nothing but h nu. So these are the two important hypotheses as against the classical hypothesis, because in classical theory on which the Rayleigh-Jean's law is based, there we assume that the average energy of the oscillator according to the classical theory it is kT, and we derive the Rayleigh-Jean's law, but it could not explain the black body radiation spectrum in higher wavelength region. So these are two important hypotheses on which this radiation law is based. Now, in order to derive the Planck's formula, what we have to find? First of all, we have to find the number of oscillators per unit volume. So whatever oscillators are there in the black body chamber, then we have to calculate the number of oscillators per unit volume, and these oscillators should lie in the frequency range between nu and nu plus d nu. This thing we have to calculate, and another thing we have to calculate is the average energy of the Planck oscillator. Means we have to calculate average energy of the Planck oscillator by considering these two hypotheses, and we have to calculate the number of oscillators per unit volume which are lying in the frequency range between nu and nu plus d nu. So Rayleigh-Jean's law is similar to the Planck's law. Only thing Planck has done is he assumed the harmonic oscillator quantum mechanically, and he calculated the average energy as against the classical energy kT. So that is the difference in the theory. Otherwise, the number of oscillators per unit volume in the frequency range which are calculated by Rayleigh's theory and in Planck's theory, they are same. Here we have to go into both, how to calculate the number of oscillators per unit volume in the frequency range nu and nu plus d nu, and average energy of the Planck's oscillator. Once you get these two quantities, then we can easily calculate the energy density, which is function of frequency or wavelength. So these are the hypothesis and what we have to do. Now, in order to calculate, first of all, we have to calculate the number of oscillators per unit volume lying in the frequency range nu and nu plus d nu. So for that, what we'll do, we will consider that the radiation is enclosed in a cubical enclosure whose walls are perfectly reflecting. So we'll consider a cubical reflector whose walls are perfectly reflecting. So that means we have to consider this as the cubical reflector, and in this cubical reflector, what we have to do, in this cubical reflector, I have to consider as this cubical reflector. So means we will consider the radiations, they are enclosed in this cubical box, and this box has the sides which acts a perfectly reflector, and the electromagnetic theory suppose that the radiation consists of the large number of waves, and these waves travel in all possible directions in the enclosure, which undergoes the multiple reflection from the walls of the enclosure. Now, because of this reflection, a stationary waves they are formed inside the wall with walls as the nodal points. These walls acts as the nodal points of zero amplitude due to the interference of the reflected waves with the corresponding incident waves. Now, these stationary waves which are formed because of the reflection from the surfaces of the cube or cubical box, these stationary waves can be compared with the vibrations of the stretched string with both ends which both ends are fixed, and the ends points of the string are two nodes of stationary vibrations, and only certain discrete frequencies of vibrations are allowed. So here we'll take some example. Suppose that first of all we'll calculate the modes of vibration in one dimension, and then we'll go for three dimension. Now suppose here the wave is propagating, and suppose these are the two points which are the node points which are at two surfaces of the cubical box, and suppose there is only one wave generated somewhat like this. Obviously this is a one mode of vibration, in which obviously this length will be lambda by 2, and if L is the length of this string, then we can write lambda by 2 is equal to L. We can write this. So this is the first mode of vibration. If suppose there are two waves, they are formed like this, stationary pattern is formed like this, then this distance is nothing but lambda by 2, and it will be nothing but L by 2. Or if there are three waves like this, they are formed a stationary pattern, then obviously this distance will be lambda by 2 is equal to L by 3. So in this way, we can write in general that in one dimension, while calculating the modes of vibration in one dimension, we can say that if L is the length of the string, then allowed wavelength, number of modes of vibrations in terms of wavelength, they will be, we can write in general, lambda by 2 is equal to L divided by N, where N is equal to 1, 2, 3, 4, and so on up to infinity. And the corresponding frequencies, possible frequencies, will be, since nu is equal to C by lambda, we'll use the value of lambda here, so that you will get nu is equal to N into C by 2L. So this will be corresponding frequencies. Here C is the speed of the wave. The wave is propagating with particular velocity, and C is that speed of the wave. Now here every allowed frequency is called as the mode of vibration. So here then allowed number of frequencies is nothing but the allowed modes of vibration. So this is the simple theory. Now this is a one-dimensional case that we have discussed, but actually we have to consider a three-dimensional because the waves are propagating in all possible directions, and that we are going to calculate. So for that, what we'll consider? For that, we'll consider a three-dimensional case. That means we have assumed that we have a cube somewhat like this, and suppose this cube is nothing but this is a black body, we can call it as, and there are a number of radiations, they are propagating in all possible directions, and these radiations are nothing but similar to simple harmonic oscillators. Now let us consider this cube has a length of each side equal to L, and we can assume that harmonic oscillators, they are inside this box. All these harmonic oscillators means they are nothing but the electromagnetic radiations, or we can call it as the black body radiations. Then this volume of this cube is nothing but it will be L cube. Volume of the cube, we can call it as V. It will equal to L cube. So it will be the volume of the cube. Now here we'll apply the quantum mechanics, particularly we'll apply the Schrodinger's equation, and application of Schrodinger equation in 3 dimension, that is the particle in rigid box, in which the energy of oscillator is given by equation. Here if you apply, the energy is given by equation E is equal to, it depends upon three integers, nx, ny, nz is equal to, and that energy is pi square, that energy is pi square h cross square divided by 2m L square into bracket, this is nothing but nx square plus ny square plus nz square. So that is how the energy is given. So it is observed that the energy depends upon these integers. Which are integers? Integers are nothing but nx, ny, nz. So values of nx, ny, nz, they are integers, excluding 0. 0 value of energy in integer is not allowed. That we can discuss in the application of the Schrodinger equation to particle in 3 dimensional rigid box. Here this n square is nothing but this nx square plus ny square plus this nz square. And also we have the propagation constant k, which is given as this is n pi by L, or you can write this as k square is equal to n square pi square divided by L square. All these things you can write. Now here we have to calculate the number of oscillators in the frequency range between nu and nu plus d nu, and then we have to calculate the number of oscillators per unit volume in the frequency range between nu and nu plus d nu. Now what we'll do, will if you calculate all possible sets of this nx, ny, nz, if you calculate all possible sets of nx, ny, nz, and if you plot in that you can call it as k space, because n is related to the k, then you will get the arrangement of the atoms, periodic arrangement of the atoms, and from that periodic arrangement of atoms we can calculate the number of oscillators per unit volume in the frequency range between nu and nu plus d nu. So for time being, I will clear this. And we will see we'll plot all these points in whatever values of nx, ny, nz, all possible values, because the energy of each oscillator will depend upon the all possible sets of nx, ny, nz, means each set will have a corresponding energy. So we'll plot all such a points in order to calculate the number of oscillators per unit volume. So we can calculate, we can plot the points like this. So these are nothing but the points that can be plotted. So each point has a particular set of nx, ny, nz. I have shown here in 2 dimension. You can consider it in 3 dimension. Means here nx, ny, lz in integer, means it has all possible combinations. Means n is equal to 1, ny is equal to 1, or n3 is equal, nx is equal to 1, ny is equal to 1, nz is equal to 1, and all possible combinations. And we'll consider here the sphere of radius n with the thickness dn, so that this is suppose the sphere I have shown, and this is nothing but n is this its radius and dn is the thickness. So n is the radius of that sphere and dn is the thickness. Now what we have to do, I have to find these number of points in this region. I have to find this number of points. I have to find the number of points in this region. I can say this shaded. So I have to find out this number of points in this shaded region. And if I find this number of points or oscillators in the shaded region, I can calculate the number of oscillators per unit volume in the frequency range nu and nu plus d. Now here, therefore, we can write as here the number of oscillators. I can write here. Oh, sorry, I can write here as number of oscillators in the range, because here the range is defined by n and n plus dn. I can write this as n and n plus dn, and that can be calculated as we can take the volume of that part, and the volume of that part is nothing but 4 pi n square dn. So that much number of oscillators in the range between n and n plus dn will be. But again, I have to multiply here by the factor 1 by 8. Why I have to multiply by the factor 1 by 8? Because you can consider the combinations of this nx as this n x positive, ny negative, nz negative. Then you can consider nx negative, ny positive, nz negative, like that. So there are 8 possible combinations, and we are taking only the positive values of nx, ny, nz, and that's why I have to take only 1/8 of the volume to calculate the number of oscillators in the range n and n plus dn. So that will be the number of oscillators in the range between n and n plus dn. It will be 1 by 8 4 pi n square dn. Now I can use the value of n square from this equation, because I know that from this equation I can write n square is equal to, I can write this as k square L square divided by pi square, or I can write n is equal to KL divided by pi. So that I will get the number of oscillators 1 by 8 into this 4 pi. I can write n square as k square L square divided by this pi square, and into this dn I can write this as L divided by pi into this dk. So that after solving this equation I will get this as, so this pi will get cancelled, and this 2 will get cancelled, L square into L, it will be L cube, so it will be L cube divided by 2 pi square into this k square and this dk. So you will get this value as L cube divided by 2 pi square k square into dk. But again we know that this k is a propagation constant, and it is given as 2 pi by lambda, and if you use the value of 1 upon lambda as nu by c, it will be 2 pi nu divided by c. So you can use the value of k here to get the number of oscillators in the frequency range between nu and nu plus d. So that's how you can calculate the number of oscillators in the frequency range between nu and nu plus d. So therefore we can write the number of oscillators, harmonic oscillators, number of oscillators in the frequency range, between nu and nu plus d nu is equal to, our equation is L cube divided by 2 pi square into this k square dk. But we know that k square is equal to, we have calculated I can write this as, k is equal to 2 pi by lambda is equal to 2 pi nu divided by c. Use value of k here, so that you will get this as, cell cube is nothing but v, volume of the cube in which we are considering the black body radiation. So this is nothing but the volume of that cube divided by 2 pi square into k square will be nothing but this is as a 4 pi square nu square divided by c square, and differentiation of this k, it will be dk is equal to 2, it will be, it will be 2 pi by c into this d nu. So simplify this, what you will get? You will get this as pi square will get cancelled. So it will be 4 pi v into this nu square divided by c cube into this d nu. So this will be the number of oscillators in the frequency range between nu and nu plus d nu. So 4 pi v into nu square divided by c cube into this d nu. However, here again we have to multiply this factor by 2, because we know that the radiation is nothing but a propagation of the electric and magnetic field in perpendicular direction, perpendicular to each other, and they are also perpendicular to the direction of propagation. So here electric and magnetic fields of the wave are perpendicular to each other. They are also perpendicular to the direction of propagation of wave, and there is an independent mode of propagation in which electric field E and magnetic field B are rotated through 90 degrees. So here you can observe here that the electric field and magnetic field, they are rotated through 90 degree with respect to the direction of propagation, and therefore any polarization of the wave can be formed by some of these two independent modes of propagations. So hence we have to multiply this factor or this quantity by 2, and so that I will get the number of modes of vibrations. So I will get number of modes of vibrations, or you can call it number of oscillators in the frequency range, nu and nu plus d nu is equal to 8 pi v into this nu square d nu divided by this CQ. But actually what I have to calculate? I have to calculate the number of modes of vibrations or number of oscillators, we can call it as per unit volume. Means we have to calculate density, and therefore I can write here the number of oscillators or number of modes of vibrations, you can call it as also number of oscillators per unit volume, in the frequency range, is equal to, I will represent this as G nu d nu, I will call them as G nu d nu is equal to, I will get this as 8 pi nu square divided by C cube into this d. So this is very important equation. So this expression is calculated, it is applicable in Rayleigh's theory also. We are using the same expression, that is the number of oscillators in the frequency range between nu and nu plus d nu will be given by 8 pi nu square divided by C cube into d nu. So in this way we can calculate the number of oscillators in the per unit volume in the frequency range. We'll use this equation while calculating the actual expression for the Planck's law. So that is how one can calculate the number of oscillators per unit volume in the frequency range nu and nu plus d. Now what we have to do? We have to calculate the average energy of the oscillator, and that is based on the Planck's hypothesis, and that is very important. These things are